Welcome to ETL 512, Electronic Circuit Analysis. Chapter 1, Introduction to Electronic Circuit. In this chapter, students will become familiar with using equivalent circuits to analyze diode networks arranged in series, parallel, and series parallel configurations. They will also learn to describe the operation of voltage multiplier circuits, which are essential for increasing voltage levels in power supply systems. Additionally, students will understand the process of rectification, which involves converting a sinusoidal AC input into a DC voltage level, a fundamental concept in power electronics. In Chapter 1, students will be introduced to the basic principles of diodes in electronic circuits. It begins with an overview of diode configurations, including series and parallel arrangements. The chapter then explores practical applications of diodes, focusing on voltage multiplier circuits such as voltage doublers, triplers, and quadruplers, which are essential for increasing voltage in electronic systems. Finally, it covers diode-based rectification methods, specifically half-wave and full-wave rectifiers, which are fundamental to converting AC signals into DC power. So what is diode? A diode is a small electronic component that allows electric current to flow in only one direction, functioning like a one-way valve. When the current flows from the anode, positive side, to the cathode, negative side, the diode conducts and allows electricity to pass through. If the current tries to flow in the opposite direction, the diode blocks it. This property makes diodes very useful in applications where unidirectional current flow is essential, such as in power supplies. Diodes are commonly used in various circuits including rectifiers, clippers, clampers, voltage multipliers, logic gates, reverse polarity protection systems, and circuits for suppressing voltage spikes. Next is diode analysis using approximation. Diode approximations are how the diodes present in the circuit gets analyzed. The diode can be considered as the basic electronic device in any type of circuit. These are of various types. A design criterion is based on the requirement. The analysis of it can be done based on the three approximations. Each approximation can be done by considering the diode as a switching element. For these basic components called diodes, there exist three approximations. In each one, the initial and the considered stages of the diode are discussed. The motive behind this is to analyze the initial criterion considered for diodes. In the first situation of approximating the diode considered to be in ideal mode. It means there is zero internal resistance and doesn't have any consuming voltage. This indicates that diode in ideal mode is a perfect version of switch. Generally, in the theoretical analysis, we can use this concept, but practically this situation is impossible. In this case of second approximation, the diode can be made to function as a switch by applying the cutoff voltages. For example, if the silicon is the semiconductor material used. Then in this case, if the voltage applied exceeds 0.7 volts, the diode is in on mode. If it is below the minimum voltage, then the diode is in off mode. Therefore, in this way diode acts as a switch. The third approximation of a diode includes voltage across the diode and voltage across bulk resistance, RB. The bulk resistance is low, such as less than 1 ohm and always less than 10 ohms. The bulk resistance, RB, corresponds to the resistance of P and N materials. This resistance changes based on the amount of forwarding voltage and the current flowing through the diode at any given time. The total voltage drop across the diode is calculated by adding a fixed voltage of 0.7 volts, which is typical for a silicon diode, to the product of the current flowing through the diode and the bulk resistance. In other words, the voltage drop is equal to 0.7 volts plus the current multiplied by the bulk resistance. If the bulk resistance is extremely small, less than 1/100th or 1,000th of a reference resistance, it can be ignored without significantly affecting the accuracy of the model. The diagrams show that in forward bias, the diode can be represented as a voltage source of 0.7 volts in series with the bulk resistance, while in reverse bias, the bulk resistance is considered alone to account for leakage currents. The graph depicts the current voltage relationship of the diode, where forward current increases sharply after the threshold voltage, and a small leakage current flows in reverse bias. This approach provides a more practical and realistic understanding of diode behavior in electrical circuits by including the internal resistance effect. Analysis of the configuration diode configuration series, parallel and series parallel configuration. Let's start with the forward bias condition. In a forward bias diode, we have a given voltage drop of 0.7 V for a silicon diode. This is an essential characteristic of the diode in forward bias. Now, let's look at the analysis. First, we need to check if the input voltage is greater than the voltage drop across the diode. This is because for the diode to conduct, the input voltage needs to exceed this threshold. The equation says that the voltage drop across the diode is equal to the supply voltage minus the voltage drop across the diode itself. In simpler terms, this means that the voltage across the diode is determined by subtracting the diode's voltage drop from the total supply voltage. This shows us how the voltage is distributed across the diode and the rest of the circuit when the diode is in a forward biased condition. Now, let's move on to the reverse bias condition. In the reverse bias condition, the diode behaves like an open circuit, which means no current will flow through it. This is because the reverse current and reverse voltage are both zero. In other words, when the diode is reverse biased, it ideally does not conduct any current. The reverse bias scenario is when the diode's anode is connected to the negative side of the supply voltage and the cathode is connected to the positive side. In this case, the diode is essentially off and acts as if it's not part of the circuit at all, behaving like an open switch. You can visualize this in Figure 1.1 where the diode behaves as an open circuit. In summary, for the reverse bias condition, the diode does not allow current to flow because it behaves like an open circuit. The reverse voltage across the diode is zero, and the reverse current is also zero. To wrap it up, in forward bias, the diode conducts if the input voltage exceeds the forward voltage drop, 0.7 V for silicon. In reverse bias, the diode acts as an open circuit, with no current flowing through it. Example 1. For the series diode configuration of Figure 1.2, determine VD, VR, and ID. Here a little hint. Check the diode turn on off. Since E greater than V, therefore the diode is turn on. Next, example 2. For the series diode configuration of Figure 1.3, determine VD, VR, ID. Here's a little hint. Check the diode turn on off. Since E less than V, therefore the diode is turn off. Establishing the open circuit equivalent as the appropriate approximation. Next, example 3. Determine V, O, and I, D for the series circuit of Figure 1.4. Given that red light emitting diode, LED, forward voltage is 1.8 volts. Here's a little hint. Draw equivalent circuit. Next is example 4. Determine I, D, and V, O for the circuit of Figure 1.6. Here's a little hint. Determining the direction of the diode. It shows that one is short circuit, forward bias, and the other is open circuit, reverse bias. These two combination always resulting in an open circuit, therefore, ID equals 0 amps, VO equals 0 volts. Moving on to parallel and series parallel configuration. The method applied in series can be extended to the analysis of parallel and series parallel configurations. Example 1. Determine V, O, I, D, D1, and I, D2 for the parallel diode configuration of Figure 1.8. Next is example 2. Two LEDs are used as a polarity detector for the source. When supply is positive voltage, the green LED will be on, and when supply is negative, the red LED will be on. Find the value of R to ensure a current of 20 mA through the on LED. Both diodes have a reverse breakdown voltage of 3 volts and an average turn-on voltage of 2 volts. Next is example 3. Determine the voltage V(O) for the network of figure 1.22. Initially, it might appear the applied voltage will turn both diodes on because the applied voltage is trying to establish a conventional current through each diode that would suggest the on state. However, if both were on, there would be more than one voltage across the parallel diodes, violating one of the basic rules of network analysis. The voltage must be the same across parallel elements. Lastly, example 4. Determine the currents I1, I2, and ID2 for the network of figure 1.23. That's all. Thank you and see you in the next video.